linked lists, but we also have a previous pointer, which is going to point at the previous node in the linked list. So with 3 nodes, 1, 2, and 3, the next pointers are going to be connected to the next node in the linked list. The previous pointers are going to be connected to the previous node in the linked list. Now the first node does not have any previous pointers, so it's going to be set to null, we can assume, the same way how the last node has a next pointer set to null. That's how we know we get to the end of the list, and this is how we know we've gotten to the beginning of the list. Now just like with singly linked lists, let's assume that we have a head and a tail pointer to the first and last node of our linked list. Now let's say we wanted to add a new node to the end of the linked list. It would be very similar to doing it with a singly linked list, meaning we would take the next pointer of our current tail node and assign it to the list node 4. We would also want to set the previous pointer of this node to be at list node 3. We would also want to set the previous pointer of list node 4 to point at list node 3, because we want to make sure that this is doubly linked. We want to preserve the properties of our doubly linked list. And then we would take our tail and shift it to the new node that we just inserted. This is how the code for that operation would look like. We would first say tail.next is equal to the new node that we're inserting. We're connecting the pointers, we're adding that node to our list. We're also connecting the previous pointer of that new node. The previous pointer should be set to the current tail. Remember, our tail pointer was originally pointing at node 3, so that's what our previous pointer is going to be set to, but finally in the end we take our tail pointer and set it to the next node, which is going to be list node 4 from the assignment we did right here. The one thing to note is the order that we do these operations in is very important. We have to do this operation before we update the tail pointer. So now let's look at removing a node. Let's remove the last node from our list, and it's a little bit easier with a doubly linked list because we're allowed to look backwards. Assuming we only have a pointer to the tail, that's actually all we need. We don't need a pointer to the previous node because from our tail, we can follow the previous pointer and it's going to take us to the previous node. This is really convenient. With a singly linked list, we would have had to start at the beginning and then kept going forward until we got to the node that we wanted to be at. We would start at the tail, follow the previous pointer, we would be at list node 2. We would take the next pointer of it, which is now pointing at list node 3, and we would instead point it at null. And it's really that simple. Now we have a linked list of size 2. Technically, this node still exists and its previous pointer is pointing here. But if we take our tail pointer and set it now to be here, as far as we're concerned, this node doesn't exist anymore. Technically it does, but we have no references to it, so we're never going to see it ever again. And depending on the language you're using, garbage collection might delete this automatically for us. And the code for that operation would look something like this, where we create a variable called node2 and we assign it to tail.previous, which is going to be here. We didn't originally have a pointer to this node, so we created one by taking tail and getting the previous pointer. Now we're taking the next pointer of this node and setting it to be null. It used to point at node 3, now it's not pointing at anything. That means that this is the new end of our linked list. So we should take the tail pointer and set it to node 2 as well. At this point, we have a doubly linked list of 2 nodes left. By the way, we did a few operations, but we didn't have to loop through the entire linked list. Regardless of the size of the linked list, this delete last operation is always going to be the same. It's going to be a constant time operation. So with doubly linked lists, we can insert a value at the end and we can remove a value at the end. So we can do both of those in constant time. Doesn't that satisfy the requirements of a stack data structure? Yes, it does. That means that stacks can be implemented also with linked lists, just like they can be with arrays. But it's a lot less common to implement stacks using linked lists because with our original dynamic array, we could pop and push to the end of the array efficiently, but we could also access any arbitrary element of the array. This is a downside of linked lists, whether we're talking about singly linked list or doubly linked list, because we can't just arbitrarily access the second element or the third element or the seventh element. We have to follow our pointers to do that. That means to access a random element of the linked list, it would be an O of n time operation. So if that's the case, it's probably better to use a dynamic array if we're talking about stacks because we get extra functionality that we lose when we use linked lists. So let's wrap up by reviewing the time complexity of linked lists and compare that to a operation because we might have to shift all of the elements over in either direction. Now with a linked list that looks something like this, accessing any element in the linked list is not necessarily going to be efficient. I mean, of course, if we already have a pointer to this node, for example, it will be a constant time operation, but that's not always going to be the case. If we had a really big linked list and we wanted to access any element in the linked list, in the worst case, we would have to start at the beginning of the list and then keep incrementing, keep iterating through the list until them as well. Remember, if we have a linked list that looks something like this, if we want to remove the middle element, we don't have to now shift everything over. We don't have to take all of these and then shift them over by one. All we have to do to remove an element like this one is take the pointer. It's currently pointing at that, but the caveat, and it's a really big one, for us to remove any random element, first we have to arrive at that element. We need a pointer to the element before we can remove it. So in most cases, we're going to have to start at the beginning, keep iterating until we find the element that we want to remove and then remove it. So while doing the insertion or removal is efficient, usually we have to iterate through the linked list before we can do that. So in most cases, it's going to be a linear time operation. So we can see that linked lists do have a slight benefit compared to arrays, but I'll be honest and say that arrays are much more common and much more useful for problem solving. Being able to access the ith element, any arbitrary element, very efficiently is really, really important, much more than something like this, especially when most of the time we do this, we're not actually going to be able to do it in constant time. We're going to have to iterate through the linked list. These are a couple very fundamental data structures, and I can't wait to show you even more. Now, so far we've talked Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem design browser history. We're given a single browser tab and we want to basically simulate the behavior of navigating between browser pages. We know that a page is represented with a URL and we will be having some starting home page for us that will be provided to us, and we'll take care of that in the constructor. Now there's three main operations that we want to support. One is pretty simple. We want to visit a particular URL. Of course, you can do that with a browser. So suppose that A is our home page, then we can visit another page. Let's say B is the page that's provided, then we end up on a second page. Now, the interesting thing here is that we have two more operations where we can move back and we can move forward in the browser history. Similar to how you can do it with a real browser, we know that if we navigated from A to B, we can always move backwards. And if we do that, we end up at... Hey everyone, just to clarify, the back forward in the browser history. Similar to how you can do it with a real browser, we know that if we navigated from A to B, we can always move backwards. And if we do that, we end up at this page, at the previous page. And if we do that, we can also move forward in the browser history. And then maybe after we move forward, we can navigate to a new page like C. And just to clarify, the back and forward operations are not just done by moving one step. Suppose we're at B, we can move one step and go to C. And then from C, we can move one step and go to B. But we could also, being at C, we can move 2 spots back to A. We can move an arbitrary number of steps, either backwards or forward. A couple quick edge cases, imagine we are at C and the number of steps provided for us to move backwards is 2, while we would move to A. But what happens if the value is 3? What happens if we try to move 3 steps backwards? Well, we end up nowhere. We end up out of bounds. So if we're given a value that's too large, then we just move as much as we can. We tried to move 3 spots, but we couldn't, so we just moved 2 spots instead and got back to the beginning. That's pretty simple. And the same thing would happen if we were at A and we wanted to move 3 spots forward. Well, we'd be out of bounds. So instead we just move as much as we can. We move 2 spots and then end up at C. So I think that's not too complicated. Now there's one last edge case. Well, not really edge case. It's more about the main behavior of the visit operation. Suppose we are at position A. We're at this page. We know we have our portion of forward history, but what happens if from here we try to move to a different page like D? Well, then we end up at D. Now, we should be able to move backwards to A, which we can, but we can't really move forward anymore because this was kind of a different branch of our history. We can't really go back here, and just like in a real browser, we want this to simulate that. So what happens is all of the forward history at this point when we visited a new page is cleared. So all of this is gone, and that's pretty much the main behavior that we're going for with this problem. Now, there are two main ways of solving this problem. One is kind of like I'm showing with a linked list, because as you can tell, we want to be able to move in both directions. So we want to be able to move forward, which you can with a singly linked list, but we also want to be able to move backwards, which you can with a doubly linked list. So that's how I'm going to be implementing this solution. It's pretty rare that we get to use a doubly linked list, so I think now's a good opportunity to do so. But I want to mention that we can also solve this problem with a stack or a dynamic array, and I'll touch upon that at the end. That's actually the more efficient way to solve this problem. And very quickly, I want to mention, what would the time complexity be for each of these operations if we did it with a linked list? Well, how exactly would we implement each of them? As you could tell, the visit operation is pretty much always going to be constant time, because no matter where we're at, whether we're all the way at the beginning of our history or at the end, it doesn't matter, because we're visiting a page. Anytime we visit a page, all we really have to do is say, okay, the next node after this current node that I'm at is going to be whatever the new page happens to be. In this case, maybe it's D. That's always going to be easy. Now, the less efficient operations are going to be these two, where we have to move backwards or forwards. With a linked list, we can't just index a random position like we can with an array. That's the downside of this approach, because if we want to move backwards or forwards, depending on the number of steps, this could be arbitrarily long. So this is an O of n time operation, where n is the size of the doubly linked list, because we might have to traverse the entire list. If we were to implement this with an array, we would actually be able to get each of these operations down to constant time, which I'll show you at the end. Okay, so now let's code it up. The first thing I want to do is create a linked list node class. So I'm going to create a class called list node. It's going to have three fields: a value, which is going to be the string for the URL that we're currently at. We're also going to have two pointers, a next pointer. Well, this is the previous pointer, and a next pointer. And by default, these 2 pointers are going to be set to null. So now to initialize our browser history, I'm going to create a current pointer for whatever current page we happen to be at. I'm going to create a list node. I'm going to pass in the home page as the value, and I'm not going to pass anything in for the previous or next node, because that can just be set to null. Now let's move on to visit, which is pretty straightforward. What we want to do is create a new list node for this URL that we're given. we're going to just pass in the URL. And before I get to the previous and next pointers, what are we doing with this node? Well, we know we're currently at self.cur. We know our current node is not going to be null because we did initialize it with a home page. And we know that whenever we move back, we're never going to go out of bounds. So we can pretty much assume that our current pointer is never going to be null. So what we're going to do is say our next pointer for current is now going to point at this new node that we just created it. So what we can say is that our next pointer is going to point at whatever new node that we just created is. Since we are creating a doubly linked list, we also want this new node to point back at the current node. So we want the previous pointer of this new node to point at cur. So what am I going to do? I'm going to say previous should be self.cur. And I'm not going to pass anything in for the next pointer because it just needs to be null anyway. Because this new list node is going to be the last node in our linked list now. Also, since this is the last node and this is also the current node, we can set self.cur equal to self.cur.next. So not too bad there. Now we also have the back operation. So while our current pointer is not non-null and steps is greater than 0, we want to set self.cur equal to self.cur.previous because we're moving backwards this many steps. We should also decrement the number of steps. So we're going to keep moving backward as much as we can. Until we've either moved back this many steps or we somehow ended up out of bounds. But remember, we never want to end up out of bounds. Instead of letting self.cur somehow equal null, we should instead say while self.cur.previous is non-null. This way, we will end up stopping as soon as we reach the last node. If we see that the previous node is null, that means we reached the last node that we could move to, or at least the first node since we're moving backwards. And once that is done, we want to return self.cur.val. This part kind of tripped me up because I forgot we actually had to return a value here, but we do. We have to return the value that we ended up moving backwards to. The forward operation, thankfully, is pretty much the exact same as this, except we're going to be moving in the other direction. So I'm going to go ahead and copy and paste this. And instead of looking at the previous node, we'll be looking at the next node, and steps will still be decremented by 1. But instead of moving backwards, we're going to be moving forward. And that is pretty much it. So now let's run the code to make sure that it works. And as you can see, yes, it does. And it is pretty current node, we can set self.cur equal to self.cur.next. So not too bad there. Now we also have the back operation. So while our current pointer is non-null and steps is greater than sounds, instead of letting self.cur somehow equal null, we should instead say while self.cur.previous is non-null. This way we will end up stopping as soon as we reach the last node. If we see that the previous node is null, that means we reached the last node that we could move to, or at least the first node since we're moving backwards. And once that is done, we want to return self.cur.val. This part kind of tripped me up because I forgot we actually had to return a value here, but we do. We have to return the value that we ended up moving backwards to. The forward operation, thankfully, is pretty much the exact same as this, except we're going to be moving in the other direction. So I'm going to go ahead and copy and paste this. And instead of looking at the previous node, we'll be looking at the next node, and steps will still be decremented by 1, but instead of moving backwards, we're going to be moving forward. And that is pretty much it. So now let's run the code to make sure that it works. And as you can see, yes, it does. And it is pretty efficient, beating 69%. There's actually a more efficient solution. Let me quickly show that to you. I mentioned that there's a solution using an array, and this is that solution. We're actually using an array slash a stack. So we don't need a linked list. Our self.history is going to be equal to an array with just a single value, which is the home page initially. We also have 2 pointers. One I'm calling I, but you could consider it our current pointer, the same as we had for our previous solution. So this is going to be pointing at the current page that we're currently at. We also have a variable to maintain the current length. The reason I have a separate variable everyone. We have to return the value that we ended up. Let me quickly show that to you. I'm going to start with the b equal to an array with just a single value, which is the home page initially. We also have two pointers. One I'm calling I, but you could consider it our solutions. We're looking moving backwards to the forward. This is going to be pointing at the current page that we're currently at. We also have a variable to maintain the current length. The reason I have a separate variable for this, and we can't just take the length of our current array is because this pointer is actually going to be the true length, or at least the length that we consider to be the real length. We don't consider the length of this array, and you'll see what I mean in just a second. Now, I'm going to start with the back and forward operations first, because they're actually more simple. Of course, if we have an array and we want to move backward this many steps, we don't have to shift a pointer, because with arrays, we can just calculate the new position. We know that I is our current position. So if we take I and subtract the number of steps, we will have the new index. But the problem is this could be out of bounds. So what we need to do is have an if statement to make sure that this is not less than 0. Now, an easier way to do that is to just take the maximum of whatever this happens to be. Maybe it's bigger than 0, or maybe it's less than 0. If it's less than 0, this equation, this operation will be set to 0. If this is greater than 0, self.I will be set to whatever value this happens to be. And then we just take that pointer and return self.history. Notice how moving backwards does not change the length of our array, because moving backwards does not delete anything. Same as moving forward. We do not delete anything. We're doing pretty much the same thing. Self.I, except we're adding the number of steps, and instead of taking the maximum, we're taking the minimum, because we don't want this value to go out of bounds in the other direction. We don't want this to be greater than self.length minus 1. This is our length variable. I'm not taking the length of history. You'll see why I'm doing that when we look at the visit operation above. In summary, this forward operation is almost exactly the same as the backwards operation. Now, this is where the actual complexity comes from. Well, there's not much complexity, but these both were constant time operations. Clearly, we're just indexing an array, and this is the same thing. Clearly, we just have a couple conditionals, and we are just, doing basic operations and indexing an array or appending to an array. All of these are constant time operations. But what are we doing here? Well, remember, when we visit a URL, we're pretty much erasing the forward history. But if we actually manually erase the forward history, like we pop every value from this self.history stack or array, we could do that. But the problem is that that would end up being an O of n time operation. We actually don't need to do that. We don't need to delete those values. We can sort of soft delete them. What I mean is, first, we know we need to add this URL to the next position. By next position, I mean the index I plus 1. So that's what we're going to do. We can only do that if that position has already been filled before, because otherwise we're going to get an index out of bounds error. So I first make sure that the array self.history is long enough. Initially, it won't be long enough to insert at the index 1 position. So we have to make sure that it is. And if it is, then we do this. Otherwise, we append. We can't just index this because we'll get out of bounds error. But that's pretty much it. And then once we do that, all we have to do is increment our I pointer because we're now at the next position. And we set our length equal to I plus 1. That's just kind of how, math works for arrays that are indexed starting at 0. And that's pretty much it. The reason we're then updating our self.length is because of this forward operation. Basically, when we set this equal to I plus 1, before that, it will probably be equal to some bigger value. Before that, it may be equal to an even larger value. Like, for example, if we have some values 1, 2, 3, and 4, but our current position happens to be over here at 2, and we want to insert a new value, something like 5 maybe, then we'll insert that 5 over here. At the same time, we want this forward history to be deleted. Instead of manually deleting it, we'll just be updating a pointer instead so that we consider this value to no longer be there, even though it is taking up memory still. So that's a new value, something like 5 maybe, then we'll insert that 5 over here. At the same time, we want this forward history to be deleted. Instead of manually deleting it, we'll just be updating a pointer instead so that we consider this value to no longer be there, even though it is taking up memory still. So that's basically how we can get this to be the most optimal solution. I admit that this code might not be super easy to understand, especially if you're a beginner, and that's because I'm kind of using some tricks that you might not be used to yet. It's okay if you have to kind of write out longer code. You have to write out some if statements here, and maybe even the first time you solve this problem, you do have to write it a less efficient way or a different way, or maybe you just have some bugs. That's okay. But I did want to show you the most optimal solution. If this was helpful, please like and subscribe. If you'd like to see the code in a language other than Python, you can check out neetcode.io. Thanks for watching, and hopefully I'll see you pretty soon. Hey everyone, welcome back, and let's write some more neat code today. So today let's